Okay, so I will attempt to present and see how this goes.
So if you're using Google Slides, it's the most convenient to just present a single tab, but if you have the whole screen, whatever works for you.
Okay, okay, can you guys see my presentation, and is it in full screen mode? The only problem I've had with Google Slides is that full screen mode is sometimes a bit finicky.
That looks good to me.
Okay, can everyone see?
Yep.
Cool. All right, sounds good. So I'm going to be talking about cloud data warehousing, and I think many of us in the machine learning space, actually I don't really count myself as being in the machine learning space anymore, but I overlap with it. I do a lot of work in data engineering, and I think a lot of us in the machine learning space, though, have developed kind of an allergy to SQL and to SQL-based tools. And so I'm going to make the argument today that if you're interested in machine learning engineering, there's a lot to be gained from leveraging these various cloud data warehouses. And in fact, they have a lot of characteristics that the older cloud data warehouses didn't have. Like they handle large text data extremely well, and they're highly, highly scalable, and they're generally good for big data problems. And I'll talk about a couple of what I consider to be best-in-class technologies. This is not going to be an exhaustive survey, but we'll talk about really 4 main technologies today. And then I think things we'll discuss today probably relate to other cloud data warehouses that I'm not going to bring up. And hopefully we'll give you a foundation for your own survey. If you're a CTO or a machine learning engineer evaluating some of these technologies, hopefully the characteristics we'll discuss today will be a good basis for you to go through that evaluation and figure out what strengths and characteristics you need to prioritize for both your production use cases and for your R&D use cases. So I've been in the data space for a while now. I originally was an academic, so I used to teach math, and then I got into data science at overstock.com. And then eventually I kind of migrated into data engineering, and now I run with Joe Reese, a data engineering consulting company. And so this is the kind of work that we do all the time. And so I'm very interested to share with you, and I'm interested also to hear your perspectives about how these tools differ from maybe other tools you're using, and when it makes sense to use something like a cloud data warehouse versus a more data lake native tool like Apache Spark, for example. Okay, so this is my basic agenda, and most of the time is actually going to be spent on point 3, but first I want to kind of talk about SQL. And in my talk summary, I mentioned that SQL kind of has a bad reputation in the machine learning space. And so I'm actually going to open by talking about how to write terrible SQL. How do you write really bad, awful SQL? And I think part of the reason that we don't like SQL is that so much of it is poorly written. And I think when we can adopt better practices to write better, more powerful SQL that's easier to share, easier to understand, better optimized, and better for collaboration purposes. Next, I'll talk about the cloud data warehouse as a hybrid data lake. So MapReduce and Hadoop and these other technologies came about in the first place because earlier generations on-prem MPP systems, they're called, so think systems like Teradata and Oracle, were very expensive to scale, and they didn't handle the kinds of workloads that Google and Yahoo and other web giants needed to process raw text data. And in point 2, I'll talk about how cloud data warehouses address a lot of these pain points. They're not perfect. They don't do everything perfectly, but they're very good for a lot of the kinds of text pre-processing and structured data pre-processing workloads that machine learning engineers need to do as part of their workflows. So these might not take care of the final step of processing to generate a model, but a lot of the transformation and cleaning and normalization that you need to do might be done very easily and nicely in a cloud data warehouse. And then point 3, again, I'll survey a number of cloud data warehouse technologies with an emphasis on, I think it's about 8 different points I want to talk about. And this is not meant to pick a winner. It's not meant to be an exhaustive survey of technologies. It's really meant to talk about some of the market leaders right now and what the good use cases for these different technologies are for those different market leaders. Okay, so if one wants to write terrible SQL, one of the first things you should do is tell everyone around you that SQL is not a real language. And if it's not a real language, then you don't need things like version control. And in fact, you probably shouldn't think very much about collaboration because after all, it's not real programming. You're just going to like hack stuff out on your laptop or your local machine. You're not going to share with anyone. You won't do any code review. You won't review other people's code. They won't review your code. You won't solve problems together. And in addition, there's this old joke about Perl, that Perl is a write-only language, that you can write it, but you can't. No one else can understand what you write. And I think we've all seen SQL that looks like that, where it's just it's a spaghetti coded mess that no one else can untangle and only we can understand. So again, definitely do that, make it write only, make it so it cannot be understood, and avoid any kind of coding standards as well. And above all else, no documentation and no commenting. So SQL has standard syntax for commenting, don't use it. Don't put any documentation in, don't explain what subqueries are, don't explain what the query does. Okay, next thing you should do is use selectstar all the time. Of course, selectstar is super convenient if we just want to preview a table. But really, if you want to write bad SQL, use it everywhere, because that way no one will be able to see what the explicit column names are just by reading your code. And you won't alias things to rename columns to even better column names for your use case. And you can save a lot of storage space by always using selectstar, not having all these annoying column names in your code. Okay, next thing you should do is have deeply nested queries. And to be clear, I'm not talking about common table expressions. I'm talking about inline nesting. And so I think we've all seen SQL queries where you're doing a select from and then a query, and then inside that there's a select from another subquery, and then inside that there's a select from another subquery. And you can go as many layers as you want this way, and it makes your code completely unreadable, which is fantastic. Avoid documentation, don't explain what these subqueries do, and then no one can understand what you're doing. A really great way to write terrible SQL. Okay, next thing you can do. In practice, often we need to join together a lot of data sources. If you need to do that, make sure that you join them all at once in one big subquery so that it becomes very hard to read. So select from, join, 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 just some massive, enormous join that all happens in one place that's not broken down into composable steps. Let's see. Okay, and in general, we've heard that naming things is hard, right? The two hard problems in programming are naming things and cache invalidation. So if naming things is hard, why should we bother? Just make sure that you don't name things by using inline subqueries. Or if you do name them something very obscure, like query 1, query 2, something that just doesn't tell you anything about what the query does. Because that way, again, your code is very hard to read. Now, the funny thing is, I taught a SQL class over the summer, and if I saw this kind of stuff from my students, I would yell at them or at least say, hey, you can do better. Like, this is not very good code you're writing. But in corporate environments and in business environments, I see this kind of SQL all the time, unfortunately. So there's a lot of very hacky SQL where things are simply not named. Whereas in programming languages in Python, it would be expected that we would name a function something that was kind of enlightening and gave us insight. Okay, and then I'll give you a couple of bonus things that aren't specifically to do with SQL, but are a couple of other terrible ways to use databases that help to give SQL a bad reputation. So you've probably heard of an OLTP versus an OLAP. And so an OLTP is an online transaction processing system. And so like the original Oracle database that became extremely popular starting in the 80s was an OLTP. It's very optimized for processing lots and lots of small transactions. So think a bank that has all kinds of transactions and individual payments happening all day long. They would process those in an OLTP. And so if you want to get frustrated with your database, use an OLTP for big data analytics workloads. In other words, take one of these systems, cram a lot of data into it, and then try to run some massive query where you select a lot of data and run some statistical metric on it, or where you're trying to do really big, complicated ETL. And then if you do this and you cram a lot of data into the system, your database is going to run very slowly because it's not optimized for this use case. And so your data transformations are going to run really slow. They'll take hours to complete. And then you can complain to your friends and colleagues about how terrible the performance is. And if you want, you can complain about how bad SQL is as well. Looks like someone posted a question here or something. Yes, I think that's very true. It's funny, like in many cases, I found that some people have a good sense of how to write SQL and they can knock it out and solve a problem quickly, but there's like no documentation. And so it's not shareable with anyone else. And I think an important thing to understand is that as an engineer, you are an individual contributor in many cases, but you're also part of a team. And so part of your job is to write code that not only runs, but communicates with other people so that it can be carried on to future projects, for example, and someone else can debug what you've written if you leave the company. Okay, so bonus number 2 is kind of the opposite. So something I've seen quite a few times. So an OLAP is an online analytics processing system. And all the data warehouses I'm going to talk about today are considered OLAPs. They're designed for not for large numbers of individual small transactions, but they're designed to scan huge amounts of data. So I'll give you a comparison. An Oracle system, or let's say a Postgres database, might be able to process tens of thousands of transactions per second. Okay, so really high rate of individual transactions. On the other hand, Google BigQuery can scan terabytes per second. Now, which of those two is better? Well, it really depends on what your application is. If you need to run a high rate of transactions, then you want Postgres. If you need to scan a lot of data to do big analytics processing and big data, then you want an OLAP system. If you want to frustrate yourself, run a massive number of transactional inserts and updates into an OLAP system. So hit it with like many updates every second, and then you can have a really powerful data warehouse, and you'll see it just like the performance will just crash. It will create awful performance. Or in some cases, some of these data warehouses don't let you do that. They have quota limits instead. And so instead, you'll hit the quota, and then all your changes will get rejected, and then all of your updates will just back up, and no more data will make it into your data warehouse. So it's my opinion that these things, so bad SQL writing practices, are one of the major causes of a bad reputation for SQL itself. Yes, SQL can be kind of an awkward language, right? It's very old. It was created in the 1970s. It's been extended a lot and sometimes in awkward ways. But in general, I find that if you break SQL problems into small pieces and document them carefully, you can do very powerful things. And I'll get into some of the reasons why you should consider, for some use cases, SQL over a language like Scala Spark. Scala Spark is a very powerful language. It definitely has its place. But you should also consider using Spark SQL. There are a lot of advantages to using such a portable, optimized language in your projects. And if you do it right, then it's a good communication tool, and it becomes a very powerful language. Okay, so next thing here, I'm going to talk about the cloud data warehouse as a hybrid data lake, and how we can think about it in these terms. How did the data lake originally come about? I talked a bit about this earlier, but again, Google and other companies in the early days were confronting this massive text problem. So this came from two sources. You were trying to scan the contents of the entire web, or you were trying to process a lot of logs coming out of web servers. And in fact, these are kind of overlapping problems because the web server logs tell you a lot about how popular different web pages are. And these days, that's one of the things that Google looks at to understand how they should prioritize rankings of web pages, in addition to looking at inbound links. And so companies wanted to solve both of these problems. And when they tried to do that with an MPP, so these are massively parallel processing databases, systems like Teradata that were really popular in the early 2000s, they ran into a couple of issues. So first of all, these are well adapted to traditional data warehousing, but they didn't scale so well past a certain point. And second, they weren't great for massive unstructured text. The Teradata types, there are types for large text, and I think that situation has gotten better over time. But Teradata, for example, is an awkward way to handle these large text problems. And so Google came up with the Google file system and then MapReduce as well. And so the original GFS paper was published in 2003. And then people started reading this paper, and then Hadoop development started at Yahoo in 2003 as well. And so you had this internal MapReduce system at Google, and then it started getting socialized out from there with open source Hadoop development. Okay, what does the current ecosystem look like, and how has it changed since then? Well, back in the early 2000s, these data warehouse systems, these traditional what we call MPP systems, just weren't as scalable. And now the data warehouse systems I'm going to talk about today all scale up to potentially hundreds of petabytes, and in some cases, potentially exabytes. So just enormous amounts of data that you can handle in these systems, especially where you're using object storage, where you're separating compute and storage, which is very different from the original MPP concept. The other thing these systems allow you to do in many cases is that they support native types that can handle very large strings. So for example, BigQuery's standard string type doesn't have a limit. There is a limit, which is that each row uncompressed has to be less than 100 megabytes. But the individual strings can be, as long as they're under that limit and the row is under that limit, they could be 50 megabytes, for example. That's a lot of unstructured text that you can pack into a relational database like this. And so it allows you to use a relational model, the standard row model of data, and yet still do something that resembles what you were able to do with MapReduce systems. And you can do this much more easily because you're able to use SQL as a core language. And so you're able to use this data lingua franca, which if you get good at the string operations in SQL, you can do quite a bit with that unstructured text. Of course, the one limitation is that I would consider this semi-structured data because you still have to figure out how to slice it up into pieces. And there are applications where that becomes awkward enough that maybe you want to use a data lake approach instead. But if you can find a nice way to slice the text up, then it can be loaded into a database like this. Okay, I'm going to show you one example real quick. I'm going to switch windows here, and so if you can't see my other window, then just let me know. I think. Okay, can everyone see? It should be coming on anytime now. Okay, just let me know if you can't see. Okay, and you'll notice tonight that I'm going to do a couple of my demos in GCP with BigQuery, and that's mostly because it's the easiest thing for me to get up and running quickly. So Snowflake takes slightly longer. It's still pretty quick, but I can just jump in and do some quick demos here with very little work. All right, so I'm going to search for the BigQuery service, and I'm in the GCP console. And if you have a Google account, you can add billing information and get to the GCP console very quickly. And you also get some free credit if you haven't done that before. And what I'm going to do is look at the GitHub public data sets, which are just shared through BigQuery. And there's a data set here called contents. And what this contains is raw text files, basically, which is kind of amazing, right? That you can pack all these raw text files in a database. The thing to understand, there are some limits here. So they limited the text file size to under 1 megabyte. So they're well below the BigQuery limit, probably so the table doesn't get too obscenely large. But the table size here is 2.3 terabytes. And so this means that if I want, I can run a SQL query to search all of these 1 megabyte or less text files that are coming from GitHub from all these software repos. If I go to the preview, I can see some of this raw data. Now you'll notice that by default, let's see. Yeah, these are truncated right now. So I'll just click show full values. And you'll notice that some of these text files I can get are really enormous. So let's see, 1 megabyte, they typically estimate is like 1,000 pages of text or so. And so that's all just stored right here within the database itself. And again, I'm able to query that with SQL semantics. And so I can do a lot of the kinds of things that I used to try to do with like Hadoop and MapReduce. Of course, behind the scenes, these databases use MapReduce like paradigms, so that's not surprising. But the kind of surprising thing is that it's now so easy to get to such massive amounts of text to data without having to spin up your own systems to do it. Okay. So if you're interested, go try that at yourself and hopefully, spin up Snowflake too to look at some of their shared data sets and see what you can do with them in terms of writing simple SQL queries. I need to switch back to my presentation. Just a second. Let's do this. Okay, again, let me know if you can't see. All right, so I want to make the case that SQL is a very useful language. I've kind of done that already. But first of all, a lot of the problems we're interested in with machine learning fundamentally have some data structure still. And where you have, sometimes you're forced to go to a data lake paradigm. So data lakes are really great when we need to handle heterogeneous data, like data that just won't fit into rows at all. But as we've seen, we can fit some pretty heinous data into these rows. And that allows us to use very simple SQL semantics, very familiar SQL semantics to process it. And so for tasks that we have to do as a prerequisite to doing more complex machine learning, various things like filtering, parsing, and normalization of raw text data, SQL is a very nice tool for that. It's very quick, it's inexpensive, there's low operational overhead to run these systems, and it's extremely portable. And I'm going to make the argument for portability later as well. And part of that argument is that even though 2 of the systems I'm going to talk about tonight are proprietary, actually 3 of them, I guess, although 2 of them have, yeah, I'll come back to that. The SQL language itself is very portable. And so if I'm using Amazon Redshift, for example, I have to do some work to move my SQL code over to Snowflake or over to BigQuery, but it's not terrible. It's a small amount of work versus greater lock-in that I might get with other languages. And so it becomes a nice core language. The other nice thing is that this is an excellent layer for data exploration. And so with SQL, if I'm a machine learning engineer handling a new problem, I can take a look at the data in the database and quickly get a sense of the data by running a number of SQL queries to explore what's going on. Okay, so these are the 4 technologies I'm going to talk about tonight. And again, this is not meant to be exhaustive. I'm not meaning to talk about every possible data warehouse or related technology. Like Databricks and Spark kind of overlaps into the data warehouse space to some extent. I think Databricks has done a very good job of managing schemas and making Spark more accessible like a traditional data warehouse. But my goal here is just to survey some of the market leaders and especially technologies that I consider best in class in some certain area. And so in some cases, this is a bit niche, but it might be a niche that applies to your particular business problem. So that's why I want to talk about these things. And I'll evaluate them on a number of different criteria. And again, I'm not going to pick a winner, except in each criteria, I'll kind of pick a winner, or sometimes there will be ties. And I'll explain my reasoning and also explain the caveats for that reasoning, depending on your particular use case. And actually, I'm not going to say a lot about Redshift, to be perfectly honest, and let me explain why. So Amazon Redshift came on the scene, I want to say it was like 2012 or so, and it was a huge hit. People saw this, they played around with this, and they're like, wait, so all I have to do is click a couple buttons, and I have this data warehouse, and I can scale it up and down over time as my needs change. That was just a revelation when it hit the market. The funny thing is that there were other data warehouses coming out, cloud data warehouses rather, coming out at about the same time, but they just never got quite the traction that Redshift did. And a lot of that probably has to do with Amazon's market share, plus the accessibility. If you're already in the AWS console, click a button and you're good to go. So Google released BigQuery at about the same time, but it just didn't catch on a lot in the early days. I think it's caught on quite a bit more since then, and I'll talk about what its particular advantages are relative to Redshift. I think the current status of Redshift for me is that if I were starting from scratch and I had no particular reason to choose Redshift, it's probably not one of the options I'd evaluate. Here's why. It's kind of the least modern of all the cloud data warehouses out there right now. And so behind the scenes, it's built on columnar Postgres. It doesn't really scale to 0 like a lot of the other options that we'll talk about. So Snowflake and BigQuery in particular scale to 0. And so there's this notion of only paying for the time that you're actually running queries or running the warehouse. Now, Amazon has done a good job of adding new features to be more competitive with Snowflake. The problem is that those features are a bit awkward to manage. And so it feels a bit like you're bolting on components to this core architecture. what I would say is if you're very invested in the AWS ecosystem and you want to stay with like AWS native products, then give Redshift a whirl. If you have already developed a lot of expertise in Redshift, then also it's probably a good option. It's just if you don't have those points of reference, then I probably wouldn't spend too much time looking at it, because I think newer warehouses just feel more, including BigQuery as it turns out, feel a little bit more cloud native, and the features, the powerful features, are more accessible with less work than you have to use in Redshift. So we're mostly going to be focusing on these three tonight, and they each have key advantages, and that's why I've chosen these three, because I think in certain ways they're each a market leader and a best in class. And the last one, so Snowflake, you've probably heard of as of recently with an obscenely huge IPO. Google BigQuery you probably heard of, and so BigQuery was an outgrowth of various internal Google data projects. In particular, they developed BigQuery off of Google's next-gen file system. So I talked about GFS. The next-gen file system was called Colossus, and BigQuery was an internal log processing tool, which is interesting, right? That ties in with the text processing use case that I was talking about. It was an internal log processing tool that ran on top of Colossus for querying massive log data sets, and then they eventually opened it up to the public. And Imply actually has a very specific use case. So it's the best lambda architecture on this list. And I'll talk later about what that is and why, if you're a machine learning engineer, you should be aware of it, and it might fit certain business problems extremely well. So it overlaps into the data warehouse space, but it has a very specialized niche area where it's definitely best in class. Okay, so if you're a CTO evaluating different technologies, let me give you a word of warning. There are a lot of garbage benchmarks out there. And what I mean is that there are a lot of these benchmarks where someone from a company, they get sponsored by a company, or they're an engineer at a company, takes their technology and tunes it, and then says, oh, it's 1,000 times faster and 50 times cheaper than this other technology. Usually these benchmarks are frankly junk. And these are two of my greatest hits. And if you're interested, I can tell you why they're garbage. But here's some things to look out for if someone throws a benchmark at you. So first of all, watch out for benchmarks that use 90s style data sets. So what I mean by 90s style data set is they're using a very small data set for this benchmark, and then they're claiming to do big data. That mismatch, that impedance mismatch, is a big red flag about that benchmark. So for example, in some benchmarks, they'll claim that their data warehouse can handle 100 petabytes, but their benchmark data set is only 100 gigabytes, so a million times smaller. There's something that doesn't smell right about that. Another trick that they'll use is putting a heavy emphasis on joins. And I'll explain that joins are still very important today. Joins are not going away or going anywhere. But fundamentally, columnar data warehouses, and all of the systems we're talking about today are columnar, are more optimized to very large data sets and less optimized for joins. And so you can, for example, make SQL Server look very good by doing massive numbers of joins, and then it will look like it outperforms one of these newer systems. Well, it's like, well, what are your assumptions here? With a newer columnar system like Snowflake, there are various ways to pre-optimize joins so that they perform extremely well. In general as well, we've kind of moved away from some of the star schema assumptions that we used to have for data warehousing. That doesn't mean that joins and star schema are going away, but we're moving into an era of more hybridized schema where you choose a schema that's best optimized for the problem that you're trying to solve and for the types of queries that you're trying to run, instead of assuming that everything has to be normalized. In fact, a lot of big data sets don't really normalize very well. Like, how do you normalize the web, or how do you normalize log files? It just doesn't work so well. So definitely understand the details of how you would optimize joins on these different systems, and watch out for these kinds of tricks. Another standard trick to watch out for is if the warehouse in question, like Teradata, for example, is one where you can't turn it off. What they'll often do in their pricing benchmark is try to claim, oh, this is how much it would cost to run Snowflake 24 hours a day, and therefore it's more expensive. Well, you don't really run Snowflake 24 hours a day. You only run it when you have something to run, and you only pay for those times. And so that's where it performs better from a cost structure perspective, is where you're able to turn it off. So again, just a word of warning, if you are doing a deep technical dive, I suggest talking to experts on the different data warehouses that you're evaluating. So give Teradata a fair shake if you're looking at it. Talk to the Teradata experts, figure out what it does best and what it does poorly. Same thing for BigQuery, implies Snowflake, Azure Data Warehouse, whatever technology you're looking at. But yeah, don't get fooled by these like very manipulative benchmarks that you'll see either paid for by the vendor or actually produced by the vendor. Okay, so these are use cases that I'm interested in, and I think that machine learning engineers should be interested in as well. So the first one I'll call medium data. And medium data, for me, usually means that your queries are in kind of the gigabyte range, and you might be storing 100 terabytes up to a petabyte of data. This is very traditional data warehousing these days. There's a lot of systems out there on premises running like this. And the point is that I, as a machine learning engineer, should not be dismissive toward this, because part of my job might be understanding business data that the company has. And so this use case comes up all the time. And in fact, I would argue that a lot of businesses would benefit from taking that data warehouse and integrating it, if possible, with their big data system. And what I mean is choosing one data warehouse to rule them all, and then I can join my business data, my medium data, with my big data. But I'm going to talk about like which databases here do the best on medium data, because there's no database here that wins on all criteria. They all have their strengths and weaknesses. Next, I'm going to talk about SQL interoperability. So these systems all have their own kind of SQL dialect. Some are more portable than others. Some are easier to convert to than others. So with some of these systems, it's very easy for me to take a Redshift and convert into Snowflake, for example. Other systems, it's going to be harder. Big data. So big data is the kinds of applications I was talking about. So maybe you have petabytes of textual data that you want to analyze. Some of these do better for that operational purpose. And they're actually, in a sense, there are three winners on this one. And I'll talk about why and what the differences on those use cases are. Fourth, so elasticity, operational overhead, and scaling to zero. So that's a lot of stuff to cram into one criterion. But it turns out that these are very, very related. And I think at some point we've started to realize that ops are expensive, right? It's very, very expensive to keep a system running well. And so you can look at the base costs of licensing and servers and such, but that's leaving out a lot of your other costs. And one of the things that companies discovered pretty early on with Hadoop is that they would spend, $100,000 on servers, but then they would end up spending $1 million a year on the team to run the system. So operational overhead is actually one of your biggest costs in some cases. And so I'm going to talk about how these different warehouses allow you to minimize operational overhead, how elastic they are. So Redshift is kind of on one side where it's really not very elastic. It's hard to turn it off. And Snowflake and BigQuery are on the other side where they're very easy to scale down to zero. Another place where elasticity comes in is that elastic systems are best for small machine learning and data science teams that are doing R&D, because they want to be able to run their queries and then not pay when they're not doing things. Inelastic systems are maybe better for traditional data warehousing, where you assume that you have 50 people running queries all day long. But if you just have one team running a couple of massive queries a day, then elasticity is really going to save you a lot of money. That's the scale down part. And it also allows them to scale way, way up very quickly so that they can process a petabyte without taking several days, which is a problem that comes up for a lot of businesses. Next, I'm going to talk about lambda architecture and streaming. So lambda architecture is a way of hybridizing batch and streaming systems. And I think it's becoming more and more important. And I'll dig into that and dig into what these systems do for lambda architecture. I'll talk about multi-cloud, which databases are most suitable in terms of being accessible on multiple clouds as opposed to one or two. Data sharing, and so this is your ability to quickly share your data sets with another partner company or someone else within your organization. Data lake integration. So this comes up when we do need to use a tool like Apache Spark. How easy is it to integrate BigQuery or Snowflake with Apache Spark, for example? NoSQL. So a lot of us have Mongo databases that are generating a lot of JSON data, where the structure can vary quite a bit. Call this often semi-structured data. How well do these systems do in handling semi-structured data? And then last one is ML integration. And so increasingly, these systems building capabilities that allow them to do simple machine learning on the fly. And of course, you as ML engineers might be like, well, why do I need that? I'm too sophisticated for that. But don't overlook the value of being able to quickly run a k-means clustering or a multi-factor logistic regression on data that's already in your database to just get some quick insights, because sometimes you'll very quickly see trends emerge, and then you can either operationalize that simple model, or you can move on to something more complicated outside your database, but having some initial insights about what might work well based on that built-in machine learning. Okay, so before I talk about these criteria, I'm going to talk about architectures. This is going to be a high-level view. I won't dive into all the details, but it's important to understand architectures to understand characteristics. And so first one is Snowflake. And the important detail here is that Snowflake's database storage is built on object storage. And so that means S3 on AWS and Google Cloud Storage on GCP, for example. And I think Azure Blob Storage if you're on Azure. And this is important because this means we're separating compute and storage. And this means in particular that we can call Snowflake an exabyte scale warehouse. And by that, I mean that because you can put an exabyte into S3, you can also put an exabyte into Snowflake, because you can just load as much data as you want. And so as you're thinking about big data, that's a really crucial characteristic. And this is one of the limitations of Redshift. It does scale, but Redshift internalizes its storage. And so it's not as scalable. Now, they do now integrate with S3. It's just not quite as seamless as it is with Snowflake. It's more awkward. Query processing runs on, if you're on AWS, runs on EC2. And the query processing layer provides a lot of the performance of Snowflake. So getting data out of S3 takes a while sometimes. You're limited by network bandwidth. So essentially what happens is your query processing layer, what Snowflake calls their virtual warehouses, consist of EC2 instances with SSD storage coupled. And so if you have a lot of SSD storage, then as your database warms up, in other words, as you start running queries, you end up with a lot of cached data in that SSD storage. And then when you query data that's already cached, the queries are very, very fast. And so that's an important characteristic. And I'll talk about why, especially for medium data applications, that will make your system very, very snappy. And it's a refreshing experience to try. If you go spend something up and try it out, it works very nicely. And then the point of this layer is that they utilize a lot of cloud services to manage networking and identities and such, so that they're not worrying about all of those details they're not having to worry about all this infrastructure. They just basically borrow that from the cloud service providers. And here are the high level takeaways. So as I said, rapid data from the cluster SSD cache. And then you have this other layer, which is like S3 or some other object storage, which can scale as much as you want. And so there's no limit to the scale of how much data Snowflake can contain for practical purposes. Obviously, S3 is a physical system, has a limit, but you can store a lot of data in Snowflake. Okay, next one I'm going to talk about is BigQuery. And BigQuery is similar in a sense. It's built on top of Colossus, which is an object store, but there's no caching layer. And I'll explain why that's good and bad. So it turns out that in addition to using Colossus, this is not the same as S3 or cloud storage. So basically, BigQuery is deeply integrated into Colossus. And so they're able to use way more bandwidth than Snowflake is allowed to use with Google Cloud Storage, for example. And so even though you don't have a caching layer, there's no SSD layer, your queries will run. I'll explain when they run fast and when they run slow, but BigQuery is very good at its streaming rate. It can scan enormous amounts of data per second, terabytes per second. And that's because your queries basically have access to petabits of bandwidth, which is absolutely obscene. But they have access to this enormous amount of bandwidth going straight into Colossus. And this is a matter of vertical integration from the business perspective. So in other words, they're able with their BigQuery service to do things that other cloud users can't do, essentially. So they're kind of cheating, but you can benefit from it if you choose to use BigQuery. Now, in addition, this diagram does not explain that BigQuery is a scale to zero service. So in terms of its processing layer, it's much like Spark. It's mostly memory-based. But it's cheap because you only pay for that memory while you're actually running a query. So once your query is done, all of your resources, except for storage, get freed up and just handed off to someone else. only while your query is running are you actually using CPU in memory to do processing. Then it scales down. So the good of this architecture, and I'll talk about that here, the good part is that you're scanning data directly from the scalable storage layer. And because BigQuery makes an end run around the limits of other APIs because they have integration, you can pull large data much faster than other cloud data warehouses. The bad part of this is that because it's a scale to zero service, it has to scale up. As soon as I run a query, I have to scale up. And so that means that my queries are generally going to take at least a second to run. There are some exceptions to that, and I think there's some ongoing work to make improvements in how this works. But right now, it takes queries at least a second to run. And so you're not going to get the sub-second queries that you get from Snowflake on small queries. But you will see if you're running a petabyte query, then this system will do very, very well. Okay, last one is imply. And imply is extremely performant. It's designed for streaming applications, but it also does very well in batch applications. In fact, it's designed to do them both at the same time. Now, the important thing to understand about imply, or Apache Druid, the open source version, is that it scales extremely well. You can scale it up. I think they claim hundreds of petabytes. But it's also very expensive to scale because the storage layer, the scalable storage layer, is all on SSD. And so you're going to be paying for that SSD. And generally with Druid, you're going to leave that on 24 hours a day. And so I'll talk about where Druid might make sense for a medium to small data use case, and where for some customers, it actually does make sense to pay for this SSD storage and have very expensive big data that's ultra, ultra performant. Behind the scenes, there's another layer. So it doesn't have to replicate everything into SSD because it uses like S3 or Google Cloud Storage to handle its deep archival storage. So in other words, in order to make sure that data isn't lost, data is also written out to S3, but all queries run against the SSD storage. And so that means if a Druid node fails, then a new node is spun up, and then you have to wait for it to re-ingest all the data that was lost from your deep storage layer, from your object storage layer, before you can start running queries against that data again. Now, why am I talking about imply mostly instead of the open source version of Apache Druid? Well, my assumption here is that our goal partially is to reduce operational overhead and costs. And so I'm talking about the managed version of the open source product because you can go in, set up the cluster manager, and then spin up a cluster fairly quickly without having to be a master of Apache Druid. Apache Druid in particular is not for the faint of heart. It has numerous services that you have to connect and configure. And so setting it up on your own and getting it working is a huge headache. It's something that you would do if you're a data engineering hacker who wants to contribute to the architecture, if you're a big organization. But for most of us, it just wouldn't make sense to do that. So I'm talking about imply, the commercial version of this. Okay, so in this section, and feel free to chime in if you have questions, but I'll talk about these solutions for each of these use cases, and then I'll rank them. And this is a very opinionated take. And then I'll explain why, the reasoning behind my ranking, but I'll also explain that for certain use cases, one of the other options might be number one instead. Okay, and again, here's the list of things we're going to look at. Okay, so as a medium data solution, and again, this is traditional data warehousing where I assume that I'm mostly querying maybe a set of data that's 10 terabytes or something like that all day long. I'm hitting that a lot for business use cases. And most of my queries are in kind of the gigabyte range. Snowflake wins pretty handily. Now, I will say that imply can also do well in this space. I'm not really ranking it here because imply is more complicated to set up, and its SQL dialect is less standard, which I'll loop back to later. So Snowflake, I put as number one because you can get these like extremely snappy small queries so long as the data is already in cache. And then BigQuery comes in next. BigQuery, the queries run slower. They might take a second or two to run, or sometimes longer. But the operational overhead for BigQuery is extremely low, and I'll come back to that later. And so it makes a very good medium data solution, so long as you're not expecting the kinds of sub-second queries that you would get from like a Teradata system. Okay, next I'm going to be talking about SQL portability, but I'm sure one of the questions you guys have is like, well, what about open source? Like, why should I consider a proprietary solution if I'm used to using Spark that's open source. And here's my argument. So I think open source is very important, and it's something that you should always consider. But I've heard what I consider to be a false argument about open source as well, which is that if I only run my own open source code on the cloud, then I'm never locked in. And actually, open source, just like any other software or tool, can be very, very lock-in heavy. So for example, I run a lot of training courses on Apache Airflow. Airflow will definitely lock you in. I mean, you can take some of your Python code and move it somewhere else, but really that Airflow code is very much written in the paradigm of Airflow with very specific Airflow functions. And so if you want to take all those data pipelines and transport them somewhere else, it's going to take some time to rip those out of Airflow and move them to a different tool. To some extent, the same thing is true of Apache Spark. If I'm using native Scala Spark or PySpark, that's a very, very specific language. And I can try to port that to other data frame languages, like R, for example, but you don't really simply port that code. You really have to start over and go through each part of the code and rewrite it to move it. And so just keep that in mind, that as you are thinking about open source solutions, there is a lock-in cost there as well, and just evaluate that with all the rest of your costs as you're getting integrated into one of these tools. Now, why am I arguing that you should consider, if you like open source and if you like portability, why should you still consider one of these proprietary solutions? Well, again, a major reason is that there's less lock-in because these are SQL-based. And so that means that I can write my Snowflake SQL. It's not going to be 100% compatible with BigQuery SQL or Imply or Redshift SQL or whatever dialect of SQL, but it won't be too hard to port. I can generally port it, start doing some syntax checking. There are these guides that help you to understand the differences in SQL dialects, and I can make the port fairly quickly. But I will talk about SQL portability and kind of rank it. And the number one for SQL portability is Snowflake, and here's why. So it uses a fairly standard dialect of SQL. And second, if you are moving from another tool like HiveQL, for example, or Redshift or Teradata, Snowflake makes that relatively easy. And so it's fairly straightforward to move other SQL into Snowflake. And so it's very nice for portability in that respect. BigQuery actually uses standard ANSI SQL with extensions. Now, the extensions are always what are going to get you in terms of portability. But it's pretty compatible with other databases, but it's still some work to move. And it's more work to move into BigQuery than it is to move into Snowflake from some other system. And so that's why I put this in place number 2. Imply, in terms of its SQL dialect, it's fairly non-standard right now. And we'll see where that goes in the future. So until recently, Imply didn't actually support joins. And so it wasn't really a full data warehouse candidate. They recently added that functionality. It's very performant, but the dialect is still a bit different from ANSI standard SQL. And so I don't consider it quite as portable. On the other hand, it's probably more portable than like Scala Spark to some other framework. And I will just do a quick open source assessment. By far, Imply built on Apache Druid is the most open source. Druid itself is open source. There are some proprietary components that are very well written and useful, such as the cluster manager, and they have a nice visualization layer that runs on top of it. But for the most part, it's open source. BigQuery is fairly proprietary. They do have some open source components. So for example, BigQuery's parsing engine is called Zeta SQL, and that's open source now. And so one nice thing about that is you could write your own interop tools to analyze queries that you were going to run on BigQuery. It's also built on a lot of other things like containers, but we have no visibility into that. And so I don't know that that really counts as open source components. Snowflake itself is fairly proprietary. I'm not aware of much visible open source in the Snowflake ecosystem right now. It's mostly happening behind the curtain. Okay, next I'll talk about big data. And in terms of big data, this is where BigQuery wins. And so once you start getting into queries that are over a terabyte, BigQuery has an edge generally. Of course, the devil's in the details. It depends on user-defined functions and CPU bottlenecks and how many joins you're doing and all these other details. But in general, because of BigQuery's deep integration with Colossus storage, it outperforms not only Snowflake, but other tools that you would integrate with S3 or Google Cloud Storage, such as Spark. Once you hit that limit where those tools run out of cache, then that raw streaming rate starts to become a very important factor. And so BigQuery becomes a very fast tool. Imply and Snowflake I put together as number 2 for different reasons. So Snowflake is still good at big data, right? It's similar to Spark when you're running queries directly against S3 because it has the same bottlenecks. You're just dealing with network bandwidth bottlenecks as you're trying to stream that data out. Hold on a second. I'm going to turn off my air conditioning so you can hear me better if I can. Let's see. Okay, that should be better. Okay, Imply and Snowflake both do workman-like big data. Like I said, Snowflake gets bottlenecked by S3, just like Spark does, because it uses the underlying S3 layer. Imply, on the other hand, doesn't directly query S3 or GCS. It's not capable of doing that. Those layers are only used for durable storage to make sure that your data doesn't get lost in case of a failure. And so practice, what that means with Imply is that you have to pay for a lot of SSD storage. And so if I want to have a 100 petabyte database, I have to pay for that much SSD storage. And in fact, if I want high availability, I think I have to do twice that. So I have to maintain enough storage to maintain copies of all my data so that if a node goes down, there's no recovery time to pull it back out of S3 or GCS. But the advantage with Imply is that it is one of the fastest big data tools if you're willing to pay the cost. So if you have a high value application that's worth a lot of money in your big company, you may want to put together 100 petabyte Imply Apache Druid cluster and just pay the price of all that SSD because you get ultra fast queries for the scale. BigQuery behind the scenes still runs on spinning disks. Of course, it's tens of thousands of spinning disks working in concert, but still, you can't compete with Flash, except that it's super expensive. And so if you have the right application, then Imply could be the right way for to go with your big data applications. In general, I consider Imply more of a big stream tool than a big data tool. So in other words, a lot of events coming in, but you're not keeping a huge deep archive because it gets too expensive to do that. Okay, so elasticity, operational overhead, and scaling to 0 next. BigQuery is the best tool by far here. And again, I'm going to do a quick demonstration because it's the easiest tool to demonstrate in. But, well, I said by far, but Snowflake actually really isn't far behind. It's really not much harder to turn Snowflake egg on than it is to turn on BigQuery. Let's see. Let me just switch windows real quick so I can do a quick demo. Okay. Okay, let me know if you can't see. So you should see the BigQuery console right now. And so basically, in conjunction with showing you how elastic it is, I'm actually going to show you how easy it is to set it up. And that's very much connected with how elastic it is. Basically, BigQuery is just a service. And once you have an account set up, you can run that service at any time. It's enabled by default. And so to show you this, your steps, if you were to start a BigQuery, would be slightly different. You would go into console.cloud.google.com. You'd set up your account with your existing Google username, and then you would get a new project. So to demonstrate this, I'm just going to create a new project instead. And so a new project is like a brand new container. It's like a separate AWS account with all isolated its own assets. Okay, so we're waiting for our new project to create, and it's created now. And so it takes me to the home screen, but I really want BigQuery. And there we go. And once I get here, what am I going to do with it, right? I have this database. Well, it turns out there's a bunch of free public data. And so I can start querying that almost immediately, or I can upload like a CSV or some data of my own. So let's go in here and let's view data set, and hopefully, yes. Let's see. Where did it put me here? seems to not be letting me view it. Let me look in here instead. So if you pull up the BigQuery public data project, you can open any of these data sets and start querying them immediately. And so basically just hit query table. I'm not actually going to run a query here, but that's the idea. And that quickly, you have a database you can start querying. And that actually query your own data, it's a matter of uploading. Snowflake is only marginally more complicated. So if you follow the second link here, you can get a 30-day free trial of Snowflake. You go in, you configure your account. The one extra step that you have with Snowflake is that you have to start a virtual warehouse. You actually have to start a cluster, spins up pretty quickly, and then you can start querying. Just make sure to turn it off when you're done so that you don't exhaust your credits for the trial right away, because leaving a warehouse running does cost money. In BigQuery, in terms of costs, as you're experimenting, if you've never done a GCP trial before, you should have $300 in free credit. And always look at this number over here. They charge you $5 per terabyte scanned. And so if you were to query 2 terabytes, that would cost you $10 out of that 300, which is not too bad, but be careful. Gets to be a bigger issue if you have your own data sets that are in the petabyte size. I heard a story of one customer that ran a 10 petabyte query just off the cuff, and it cost them $50,000. So it can get expensive if you're not careful. So just be aware of that in the background. Oh no, let me say one more thing here. So in terms of cost structure, when I talk about scaling to 0, just charging per query rather than charging to have the database running is basically the core of BigQuery's scale to 0 model. And then you also pay relatively cheap for relatively cheap storage, but you're going to pay for this data you have stored plus the queries you run. You don't pay 24 hours a day to have nodes running. Snowflake, you turn on your warehouse and then you turn it off when you're done with it. And so you're only paying for the warehouse during that time when it's actually running. Imply is not really a scale to 0 service. It's not as appropriate for these use cases if you're thinking about elasticity. Okay, in my talk description, I talked about, I was gonna tell you guys why lambda architecture is important for you to think about as a machine learning engineer. So if you're a working machine learning engineer, your goal, what's your real goal? Well, it's not just to do research. It's not to play around with GANs. It's not to just do deep learning. All of those things can be part of your job, but your fundamental job is to serve the business. And so it's to deliver value to the business and to customers by using machine learning applications. And I think my goal here is to kind of broaden that mandate and say that in general, your goal is to deliver data products to customers. And those can involve deep learning. They can involve clustering. They can involve statistics. But you're trying to deliver products that produce some value for the business. And streaming can deliver a lot of value for the business. Now, one thing I will say is that I think people get a little carried away with streaming sometimes and say everything should be streaming, everything should be real time. I don't think that makes a lot of sense. Inherently, batch systems can scale better. They are more efficient. And so when you're talking about massive amounts of data, usually that needs to be handled somehow in a batch-oriented system where the data individual events have been compacted together to make sure that their storage and scanning is very efficient. And so that's where the lambda architecture emerged. And so the idea of the lambda architecture is that you combine a real-time component with a batch long-term storage component and use those together so that if I query for the last month, for example, up to the minute, I get a complete picture of my data. I'm not going to be missing the last 2 hours or 2 days of data because it hasn't made its way through the batch system yet. And so here's the basic idea of Lambda architecture. You have a stream processor, and the stream processor does two things. It ingests your currently incoming data, and it also provides a query layer. So it's basically a stream cache. And as data comes in, it gets loaded into the stream cache, and I can query that stream cache to get a picture of what's happening right now. In addition, the stream processor works with the batch processor. Where the processing happens exactly depends on the architecture, but somewhere you take the data in the stream cache and you basically compact it and make it nice for long-term storage and large queries. And so you'll take raw events and convert them into a native database format typically. And so then that data makes its way down into the batch-oriented engine. over time. And as data is compactified and prepared for long-term storage, it's removed from the stream cache. And so I can also query this batch query engine, and that could be querying petabytes while I'm querying also the last 5 minutes of data up here. And it's kind of annoying to have to query these two systems separately. And so that's where you have a unified query engine. And what the unified query engine does is issues queries both to the real-time part and the long-term part, and then it combines the results together so that I have a very clear picture of what's going on right now. And my argument here is that such architectures are, in fact, very valuable for data products. Again, not everything should be real-time, but if I'm running a retail website and I want to be looking for problems like denial of service attacks that could cost me a lot of money, a real-time system to monitor for those kinds of problems could be extremely useful. And it might be doing some kind of long-term comparison of data. So you might run a SQL query, get data going back for the past 2 days, plus up to the second data. And then on top of that, maybe you apply a machine learning model that looks for things that are out of the norms that could indicate a problem with my website, either operational or some kind of attack. Another possible application would be real-time pricing. So Amazon uses real-time pricing, and to do that, they monitor the inventory status of items plus incoming purchases and traffic to different pages. And so by being more sophisticated with the real-time architecture, you can generate value for the company. You can combine this with other machine learning techniques. Now, here's the problem. This architecture is very hard to set up, and it has a very high operational overhead. SREs, site reliability engineers, are very expensive, and their jobs are very stressful. And just being the engineer who manages something like this, even if I'm not operationally responsible for it, it's a huge job, and it gets very expensive to have a team that can handle something like this. And so what I'm arguing here is that you should let someone else do the work of setting up a Lambda architecture by using one of these off-the-shelf products instead, and then just focus on your job as a machine learning engineer. So how do I deliver value from that system? And so there are two different solutions here that offer this type of Lambda architecture. And this is where Imply is the clear winner. In fact, Imply was designed from the ground up as a Lambda architecture analytics system. And so it's designed to pull in very recent data, but also to store long-term data in a very efficient format so it can query both data sources, batch and stream, very, very quickly, instantaneously almost. BigQuery is a runner-up here. It's not designed, it's more batch-oriented, but it does have a streaming feature, and it has a streaming cache, so you can stream data in, you can query both data sets at the same time. Those queries now will probably take a couple seconds to run, at least, because the underlying architecture of the batch side is more cost-effective, in some ways more scalable, but it does rely on spinning disks. And so you have this latency overhead of doing this in BigQuery, but you can still run queries that will run in a couple seconds and give you a very up-to-date picture of your data. And so these are both potentially systems to consider if you have this kind of application. At this point, Snowflake doesn't really support a Lambda architecture. It does support an architecture where data can be loaded and show up within a couple of minutes. And frankly, that may work just fine for you for whatever application you're considering. A lot of applications benefit much more from you get a lot of gain by going down to 5 minutes, and you don't see a whole lot more gain by going down to 1 second. And so always evaluate what your business problems are and where the value is really going to be found and where you start to hit diminishing returns. Okay, next thing here, multi-cloud. So a lot of businesses are interested in avoiding cloud lock-in, or they have a footprint on multiple clouds. And so this is a problem they need to consider. So for example, Redshift is not portable at all. You can't take it anywhere. It only runs on AWS. BigQuery kind of runs on multiple clouds, which I'll talk about, and that's an evolving situation. So of these, Imply is probably your best option because, well, if you truly need to be multi-cloud, I would put Imply in the #1 spot because it's portable, right? Behind the scenes, you can just get the code if you want to and run it yourself and deploy it on any cloud you want to. In terms of having a full, nice management layer, I think that might be a little more restricted in terms of having the nice cluster manager, but it's still pretty easy to move around. Snowflake has really strong support for 3 major clouds right now. So AWS, Azure, and GCP, you can run it on any of these clouds. And I think there's even cross-cloud data sharing to some extent, which we'll loop back to later. And so it's also an excellent option as long as you're only interested in those 3 top clouds. The thing I'll say about BigQuery is that it used to be a GCP only service. They recently introduced something called BigQuery Omni, which will also let you deploy BigQuery on AWS. Now, you'll remember earlier that I said that BigQuery benefits from vertical integration. And so a lot of its performance comes from the fact that the storage layer, the Colossus storage layer, is deeply, deeply integrated right into the processing layer. And so when you run it on AWS, you lose that advantage. However, the advantage that you do get is that you now have this cross-cloud integration between BigQuery Omni on AWS and BigQuery on GCP. And so if you were in a situation where a lot of your footprint was going to be on GCP, but then you needed to query some data on AWS and maybe move it back and forth, BigQuery Omni could eventually be a good solution. I think it's only in alpha, possibly beta now, so it's still a maturing technology, and the situation is evolving. But it's something to look at, and this comes up a lot actually because many of our clients work a lot with Google Ads data and other Google Media data, like YouTube data. And BigQuery integrates directly with those data sources. And so if they have an AWS footprint plus a lot of Google data, then BigQuery could make sense cross-cloud that way, where you're going to run a lot of queries on GCP, but then integrate that data with AWS data. So it's not quite as portable, and it's not as mature, but there is a use case to be made there, I think, depending on what you need to do and what space you're in. Okay, data sharing. So what does data sharing mean? Data sharing means that I can easily take my data that's interesting to me and say you're a partner business. I can just quickly share it with you and say, here's my data, query it, join it with your data, do what you need to do, and then tell me what insights you can find, or vice versa. And so it turns out that BigQuery, oddly enough, was originally created as a data sharing tool. So internally at Google, they had the Dremio architecture that they were using for log scanning. Another team was interested in creating a data sharing product, and they realized that if you're sharing data, ideally you also have a query engine that comes with that. Really, you want to kind of be able to share the data in place so that someone can do something with it. And let me give a little bit of context. I mean, data sharing has been around a long time through APIs, but that's a very, very high friction process. So for example, if I want to share data from Google AdWords, I have to write API code, access the API, download that data, then load it into another database to actually do something with it. Whereas if the data is just shared within a database where I have access to this public database like BigQuery, then I can immediately start gaining insights, and I can also join and union that with my own data to start to see interesting things. So BigQuery is very good at this, so is Snowflake. So BigQuery original use case was data sharing. I think with Snowflake, it was one of the early, it was on the list of use cases they were interested in. And so also deeply built into the system. The thing I'll say about the two is that data sharing on BigQuery is easier, but Snowflake has more data share mindshare. So companies like Adobe are already making paid data sets available through Snowflake. You just create a Snowflake account, and then you get the right access, and then you can start querying that data. And so I think, for example, that Adobe offers anonymized web data so that you can look at traffic trends on your website versus someone else's, anonymized website, and kind of see how you're performing during certain peak times, for example. Okay, next is data lake integration. And the point with data lake integration is that I would argue there's a lot of stuff you can do with text and SQL, right? In fact, I could probably even stem and tokenize raw text data if I wanted to in SQL. But that's probably not something I should do. At some point, the SQL gets complicated enough that you're just better off with another tool. And I guess the idea with data lakes is that originally they arose to store massive heterogeneous data. So just these enormous files with no clear standardized structure. And once it was in the data lake, you could then apply different tools to it to try to get what insights you wanted. The data lake now is becoming more important mostly for the use case of applying multiple tools, right? So in many cases, I have data that I want to run SQL against, but I also want to run Apache Spark against. And that's where data lake comes in really handy. And I'll explain the issues that arise with using a cloud data warehouse with outside tools and how these problems are being solved by these different databases. So it used to be that getting data out of Snowflake or BigQuery, suppose I were just treating the database as a data lake and then I wanted to get the data back out. It used to be really, really hard. So once upon a time, I was working on a team that was using Snowflake with Databricks. And so we wanted to run these Spark jobs on our Snowflake data. And so we'd spin them up and they would take an hour. And so we tried to crank, Snowflake and go to larger and larger warehouses. And I think one time we got in trouble for spending $2,000 in a day on a very small team because we had spun up such a large warehouse and it wasn't getting a lot faster. And so researching the architecture a little more, what we found out is that at the time, Snowflake had to do a full dump. It had the data internalized in its own format, and then it had to convert it and dump it out to S3. And then Databricks, so Spark, had to ingest it again. And it was this very slow, arduous process to get the data out and then process it. And so it really did not work very well at all as any kind of a hybrid data lake or anything like this. And so Snowflake's new approach since then is to tell you, well, instead of treating Snowflake as the data lake, we'll just automatically ingest the data in your data lake that's of interest. And so what you do is you create what's called an external table. You create a table that points to data in your data lake. And then Snowflake automatically converts that into a native table using what's called a materialized view. So anytime I upload those files, it auto-ingests the latest version, and then I have a table that I can query immediately. Meanwhile, the data is still in the data lake, and so I can query it with Spark, and I'm not going to have that big latency to export into S3 or GCS and then run a query against it. So there's some overhead of running jobs and storage costs and such things, but basically it's a pretty smooth process now if you want to use Snowflake in that way. BigQuery approach is a little bit different. So what BigQuery does instead is it gives you an API for very, very quick access to your data. It's called the BigQuery Storage API. And so basically now I can connect Spark to BigQuery, and instead of waiting for my whole export job to run, it starts streaming out rows immediately. And so Spark can get to work very quickly, and it supports a lot of bandwidth. And so both of these, I consider this a tie because they both integrate very nicely with the data lake environment, where I assume that some of my data is going to need to be processed in other tools. Okay, next, NoSQL. So what do I mean by NoSQL? I mean the kind of data structure that's become popular in, for example, MongoDB, where I don't predefine a schema. Instead, code is allowed to create JSON objects and then upload them to Mongo. And then Mongo has the capability to query those JSON objects in a very native way. And so I can have my code step through the JSON object using some kind of reference notation and get to the piece of that JSON that I need. So Snowflake supports what's called a variant data type. And so what it does is it recognizes JSON or even XML and these other nested data structures, and it converts them into a native nested data structure instead. And the important thing about the variant data type is that I don't have to predefine the schema. And so if I assume that my developers are working with a lot of flexibility on a Mongo database where I don't know what the data structure is going to be in advance, or maybe they might add new fields every 2 weeks and I don't want to break my ETL, Snowflake is very good for this because it can just ingest that natively and then handle those variants inside that nested data structure. BigQuery, you can ingest JSON, complex JSON, but you need to do it in one of two ways. So you need to predefine the schema. So I need to know exactly what the nested structure looks like in advance, or I ingest the JSON just as a string, and then I use SQL functions to try to address the different components of the JSON. It works. It's not quite as native. So in other words, you don't get this ultra fast performance that you get from a native ingestion of a data structure. Okay, and last one, ML integration. So if you're interested in this, check out BQML, look up BigQuery Machine Learning. And basically the idea is that once data makes its way into my database, I have a bunch of machine learning algorithms that I can apply directly inside the database without ever removing the data. So I don't have to pull it out and get it into Spark. I can just immediately run an algorithm against that data in place. And so often you'll find that even simple algorithms like logistic regression or multi-factor logistic regression can give you a lot of interesting results. So something to just jump in and try out and check out some of the tutorials. Snowflake, I think, is adding options, but at this point, they're somewhat less mature. So the focus for them right now is more on integration with third-party tools, as opposed to having native built-in capabilities for simple algorithms. And my last recommendation here would be to just go try these tools if you're interested at all. And so if nothing else, these may be good tools for replacing some of the workflows that you're doing on your laptop right now. The advantage being that if my MacBook has, say, 512 gigabytes of storage, I go into BigQuery and I immediately have access to unlimited storage and can run SQL against a huge amount of data if I need to. Also, it means that I can start sharing it from the cloud with other people on my team without having to transport the data back and forth. So go check it out. Go check out BigQuery. Go check out Snowflake. And if you're interested in Imply, certainly read some of the documentation. It's a bit harder to spin up, but there are trial options if that sounds like something that would be valuable for your business or some of the work you're working on. And that's all I've got. So I'll stop there.
Awesome, Matt. Do we have any questions for him? Cool. I'm going to go ahead. I'll stop the recording.